Hello everyone and welcome back to PC Retro Programmer. In previous videos in this series we've looked at how to draw lines, circles and ellipses on the IBM CGA graphics card that was used with the original IBM PC. And we did this in 8088 assembly language so it would actually run on an original PC and XT and various clones. And the result was quite efficient, and I was pretty happy with the performance, and it looked okay as well. But there's one challenge that we haven't taken on yet, and that is general ellipses. So what we've drawn so far is known as a standard ellipse, which has its axes aligned in the horizontal and vertical directions. A general ellipse is similar, but rotated, so the axes could be at any angle. And this is a much harder problem to solve. It's not the sort of thing where you can just go to a website, get a nice easy algorithm, implement it in assembly language, and you're done. In fact, I think you'll find it pretty hard to find any websites that give a decent algorithm for scan conversion of a general ellipse. There are papers in the literature on this though, going back many decades, and each of them seems to have a different problem. And every time a new algorithm is developed, people are typically building on earlier algorithms and trying to solve one or other problem that appeared. And unfortunately this just hasn't converged on a nice easy algorithm for scan conversion of the general ellipse. And that's why you don't find lots of websites parroting this final algorithm. So I actually tried to do this kind of thing previously on my other channel, PC Retro Tech, but there I did it on a 386 with VGA graphics, which makes things a lot easier. First of all, there's just a single byte for each pixel, which makes that side of things easier. And in addition, the 386 has much bigger registers and much more efficient arithmetic. Even there, it turned out to be an almost impossible task. It took many weeks, and I encountered many different problems which are not obvious at first sight. But I got something that worked reasonably well in most cases. What I'd like to do in this series is something similar, but for the 8088. Now, I speculated when I did the 386 work that maybe this is actually impossible, or at least prohibitively difficult. But I think so long as we're prepared to make a couple of compromises, it might be possible to do something. First of all, we're definitely not going to be able to do everything in the CPU registers. There just aren't enough of them, and they just aren't big enough. We're going to have to use a lot of memory variables. And in addition to that, we're probably not going to be able to come up with the most efficient assembly language code for doing this. We're going to have to rely on a library of functions for doing the arithmetic, specifically multiplications and divisions, either in fixed point or floating point. And that's something we'll have to develop as we go. And we're also going to have to use some kind of tricks to deal with some of the problems that occur when scan converting general ellipses, and that's something we'll look at in more detail as the videos go by. Now, I haven't done all of this in advance, so I don't know if it's going to be possible. It's very likely that we end up getting to a point where we can draw some ellipses, but others are just out of reach. Now, if that happens, there are a couple of things that we can do. If you've ever seen any kind of general ellipse drawn on early hardware, the chances are it was a very slow algorithm that just basically took the equation of a general ellipse, plugged in x-coordinate values, solved the resulting equation, which requires taking a square root, which is very inefficient and slow on early hardware, and then just plotted the points that you get. Now this works, it's just very, very slow and not the sort of thing that we want to do here. Another thing that was quite common for faster ellipses is to cheat by just picking a bunch of points at regular intervals around the ellipse and joining them up with straight lines. So what you end up with is actually a polygon that approximates the shape of an ellipse, and you have to squint pretty hard to see that it's actually not really an ellipse but just a polygon. Another approach is what's known as a skew ellipse. So the idea here is to take a standard ellipse and to skew it in the vertical or horizontal direction. So technically what you're doing is adding a linear component to it, which sort of raises the right-hand side of the ellipse and lowers the left-hand side of the ellipse in a nice smooth way. So basically the way it works is you imagine a straight line drawn vertically through the midpoint of the ellipse. And all the points to the right of that you would skew upwards, for example, and all the points to the left of that you would skew downwards, or vice versa. And the further away you are from that center line, the more you would skew the points. And it's just done in a linear fashion. Now, this is not a slam dunk. First of all, if you can figure out how to do this, you still have to transform from the equation of the general ellipse you want to draw to the parameters for the skew that you need to do. Secondly, I don't know if you can draw every general ellipse this way. I did take the equation of a standard ellipse and plug in a transformation equivalent to this skew to see what would happen. And in fact, you do actually get an equation of an ellipse. The question is whether you can get any ellipse this way, and I suspect that the answer is most likely that you have to do both a horizontal and a vertical skew at the same time. But even supposing that weren't a problem, we still have the issue of which points to actually plot. If you take points on a standard ellipse that have been scan converted for a standard ellipse, then skewing those will end up with the errors from the original scan conversion for the standard ellipse added to the errors from the skew, and this means that you could end up with the wrong pixel in some cases. In addition to that, pixels that were right next to each other on the standard ellipse could end up stretched apart on the general ellipse after the skew, and so they're no longer next to each other, and you'd have to fill in the points in between with straight lines. And we're back to drawing polygons again. So I'm absolutely sure that there'll be algorithms in the literature that are based on scan converting a skewed ellipse directly. And that's definitely something that we should look into if everything else fails. But what I want to do in this series is to take a more traditional approach, which is just to scan convert the equation for a general ellipse directly. And there might be an advantage to doing this because it turns out that the ellipse is just a special case of what's known as a conic section. And perhaps if we come up with a method for drawing general ellipses, we can also draw other conic sections, namely parabolas and hyperbolas. So that would be really cool. But at any event, it's going to be a difficult task, and I don't necessarily expect that we'll be successful. But I think it will be fun to try, and almost certainly we're going to get something out of it, even if it has some restrictions, and we're going to learn a lot along the way. So that's what this next series of videos is going to be about. Now in today's video I didn't want to do too much, certainly no coding. I just wanted to introduce the topic and cover some of the choices that we have up front. And these, of course, depend a little bit on the mathematics, although I'm going to keep things as lowbrow as possible. Basically, an ellipse is a special case of what's known as a conic section. And these were studied by the ancient Greeks thousands of years ago. They noticed that if you take a cone in space and you intersect it with a plane cutting through the cone at some angle, then depending on the orientation of that plane with respect to the cone, you'd get three different kinds of curves as the intersection. You'd get an ellipse, a parabola, or a hyperbola. There are also some special corner cases where you just get degenerate shapes, which basically just end up being some straight lines. But if you get a curve, it's one of these three, and they studied each of these cases. Now, for the ancient Greeks, they didn't have coordinate geometry like us, so they wouldn't have written out equations for the x and y coordinates of points on the curve. Instead, they did everything with respect to some special points. So for example, in the case of the ellipse, there are 2 points called the foci of the ellipse, and they have a very special property. If I take any point on the ellipse and add up the distances from that point to each of the foci, then the sum of those 2 distances is always constant on the ellipse. This is really cool because it actually gives you a way of drawing an ellipse in practice in a very simple way. If you get 2 nails and bang them into a piece of wood some distance apart, and then get a piece of string which is longer than the distance between the nails, so there's some slack, and tie off the ends to the nails, then you take a pen and you jam it against the string, and you just move the pen about, always keeping the string tight. If you think about it, any point that you draw with the pen is going to be at a position such that the sum of the distances to the nails is equal to the length of the string. The string is not changing length, and so basically you're going to be drawing all the points such that the sum of those 2 distances is a constant, and that gives you an ellipse. It's really cool. Try it out. It actually works. Unfortunately for us, this doesn't help. We're drawing our ellipses on a computer screen which has pixels with x and y coordinates. So we really need to do things using coordinate geometry, not the way the ancient Greeks did. So this means that we need an algorithm to tell us which particular x and y coordinates to draw given the equation of a conic section. Now someone's already gone and worked out the general equation of a conic section for us, and it looks like this. You can see that there are 6 constants, a, b, c, d, e, and f, and depending on how you choose those, you'll end up with a different shape. And basically an ellipse is a special case of this. An ellipse is the case where this value, b squared minus 4ac, is less than 0. If that's equal to 0, you get a parabola, and if it's greater than 0, you get a hyperbola. So basically this ends up being then the equation of ellipse, so long as this particular value, called the discriminant, is less than 0. So supposing we have such an equation here, how do we turn this into an algorithm to give us the actual x and y coordinates? Well, I already mentioned one very primitive way, which is to just plug in all of the different x coordinates, and for each x coordinate you end up with a quadratic equation in y, and you can just solve that equation using the quadratic formula. That'll give us 2 values of y for each x coordinate, and those just give you the coordinates of the points you need to plot. Sounds simple, but unfortunately it's not efficient, and the reason is that the quadratic formula involves a square root, and square roots are really inefficient to compute on an early machine, and we'd need to do this for every x coordinate, and that's just going to be prohibitively slow. So instead we need to do things a little bit more like we did for a standard ellipse. There we broke the ellipse up into 8 octants, and the idea is that if you're drawing a curve where you're always moving more in the vertical direction than you are horizontally, then you know that each iteration you'll be incrementing the y coordinate, and the only thing left to decide is whether or not you also need to decrement the x coordinate. And so for that we introduced a decision variable which would actually tell us whether or not we should decrement the x coordinate or not every time we incremented the y coordinate. And so that's exactly how we're going to do things for our general ellipses as well. But it's a little bit different. So first of all, our shape is no longer symmetric in the x and y directions. And actually what we need to compute is the rightmost point and leftmost point of our general ellipse, which are no longer going to be on the same scan line due to the rotation that we have. And similarly, the uppermost and lowermost points of the ellipse, and we're also going to need to compute the points where the slopes of the curve are at 45 degrees as well. So basically that'll give us 8 points, which will be the endpoints of the 8 segments that we need to draw. And the first task will be to compute these 8 points. So the way it works is that the point that is rightmost on the ellipse is precisely the point where the slope of the curve is vertical. Basically we say the slope is infinite. And the point at the very top of the ellipse is the point where the slope is horizontal. In other words, the slope is 0. And that's the same for the point at the bottom of the ellipse. So that covers 4 of the points. They're also the diagonal points, and these are the ones where the slope is basically 45 degrees, either sloping up or sloping down. And those are basically where the slope is +1 or -1. The question is, how can we compute the slope? And here, unfortunately, there is a problem. And that is that we need to use a technique where if you even say the name of that technique on YouTube, at least 95% of people will unsubscribe from the channel. Trust me, I'm not going to go through a long derivation and show how this is all done. It's actually very trivial, but I'm well aware of the fact that 95% of people either didn't do calculus, that there I've said the word, or don't want to know how to do calculus. That's absolutely fine. I'm just going to give a hint about how this is done and then show the result. And the important thing is that calculus has this thing called a derivative, which is really easy to compute in the case of polynomials, which this equation certainly is. And the derivative directly gives us the slope. So we just need to compute the derivative for let's say the derivative of y with respect to x here, and that will give us the slopes, and we just need to set those values to 0, infinity, +1 and -1, and solve the equations that we get. And the equations are actually very simple to solve, and this will actually give us the coordinates of all of those endpoints of the 8 segments that we need to draw. So that's what we're essentially going to start by doing, and we'll do that in the next video. The other thing that we need to decide is exactly which equation of the ellipse we're going to use. So there can be some variation here. For example, you might set the ellipse up so that the origin is actually the center point of the ellipse. That's a perfectly valid choice and probably a good one. But there are other options, and various algorithms do it differently. So another option would be to pick one of those special points, for example the rightmost point of the ellipse, and make that the origin. So then the origin is actually a point on the ellipse. And each of these transformations has a different property. Usually it means that we can get rid of at least one of these constants here and simplify things down just a little bit. So we'll look at that as well in the next video and see exactly which choice we want to make and start working through the maths, although as I said I'm not going to go through the derivation in full, I'll just show the result. And from there we should be able to start looking at some of the problems that we're going to encounter when trying to scan convert the general ellipse. Now there's a few other issues to deal with, the first of which is just what algorithm we're going to use. For the video I did on the other channel, I used an algorithm due to De Silva from the 1980s. From memory it was his master's thesis. And it worked okay except for ellipses that were very narrow or at certain angles. What would happen is you get massive cancellation and basically you just lose all your bits. So I had to implement a bunch of different tricks to work around this, and that worked okay, but that was on a 32-bit machine. It's going to be much harder on a 16-bit machine. It already turned out to be quite a difficult task there. Since then I found a paper that aims to deal with some of these issues. from 2002. It's not very long or clear, but the main idea is easy enough, and we can certainly give it a try and see what happens. The issue is that by 2002 everyone was working on 32-bit machines, and so they weren't trying to deal with these old architectures. So whether or not those tricks are going to help us is unclear. Now, another issue that we need to resolve is whether we're going to deal with all three cases of the conic section at once. Certainly the equation is the same for all three, the only difference being the value of this discriminant. And there are algorithms that try to do all three. It'd be really cool to have the same piece of code that can also draw parabolas and hyperbolae, but it's not really clear that the algorithms that exist for this are any good. And in addition, there are going to be some differences either way. For example, for the ellipse, we'll have 8 different segments or octants, as we already discussed, and that's not the case for the parabola and hyperbola. So there are going to need to be some differences there. And if we do end up with a bunch of special cases to handle this overflow issue that I talked about, then those are probably not going to apply the same way to the parabola and hyperbola as they did to the ellipse. So we might have different problems to resolve here. So if it gets too much, we'll just switch to dealing with just the general ellipse. Now, another issue is the non-square pixels. We don't want a situation like we had with circles, where we went to a whole bunch of trouble to implement something only to discover we ended up with squashed circles. Now, in this case, I don't think it's going to be much of an issue. To compensate for this, all we need to do is to scale one of the variables by a constant value. And the effect of that will just be to change 3 of the constants in our formula. And when we do this kind of scaling, an ellipse still remains an ellipse. And so if we have code for drawing a general ellipse in this form, then it's not going to care that we had to change a few of the constants. So there are a few issues with the actual code for doing the scaling, but this is a fairly simple piece of code, and I don't think that it's going to result in too many issues. Now, another thing we're going to have to deal with is whether or not we want fixed point or floating point arithmetic. In the video on the other channel, I chose fixed point, and what this does is choose a fixed number of bits before and after the binary point and keeps it the same throughout the algorithm. Of course, you can use multiple different fixed point formats if you want. You just have to convert between them when you change. And this is essentially what I did in the other video. Basically, I used, I think, 48 bits with 16 before the binary point and 32 after. And then for some points of the algorithm, I used 64-bit with 32 bits before and 32 bits after. And this worked out alright in the end, but of course on a 16-bit machine, a 48-bit value is already 3 full registers. And so if you have a value, something you're multiplying it by, and the result, that's a lot of registers. So probably we're really going to want to restrict ourselves to a much lower precision, and that's the remaining issue that we have to decide. Now, the alternative would be to use floating point, and for this we might actually get away with 32-bit floating point. The way floating point works is to adapt the position of the binary point depending on how much data you actually have above and below the binary point. And so the result that you get from this is typically quite good. The disadvantage is it's much slower. And that's because obviously that adaptation that you have to do really costs quite a bit of effort. So it's a little bit harder to implement the actual floating point routines themselves, but the other advantage is that the whole algorithm then becomes conceptually easier. You don't need to deal with all these special cases to deal with overflow. Basically, if you end up with a lot of overflow, you just have to increase your floating point precision. But we'll end up with a slower result. So I think basically what we'll do is we'll start with fixed point. If that proves to be prohibitively hard, we'll switch to floating point. If that still doesn't work, well, we'll try something else. So that's the plan of attack, and that's basically where we're headed with the remaining videos for this series.